Here we're going to take a look at the Stormville free response question that we completed in class. We're going to look not just at the answers, but also at the solution methods behind those answers. Make sure that before going over this video, you actually take a look back at the questions, think about them, either look back on your correct solutions or complete the ones that you did not get to on your own. All right, this problem can be made a lot easier if you make some key insights in the introduction. A cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. That's big because we know that the radius of the cylindrical can is constant. The can is initially empty and rain enters the can during a 6-day period. This is important. This is telling me an initial condition. The height of the water in the can is modeled by the function s, where s of t is measured in millimeters and t is measured in days between 0 and 60. So combining the initial condition and the fact that s is measuring the height, we know the can is initially empty, meaning the height is initially 0. So we can say that s of 0 is 0. And we are then told that the rate at which the height of the water is rising in the can is given by s prime of t, which is that trigonometric function right there. Okay, so with this in mind, we can draw a little picture of our cylinder. Important things to annotate, obviously, are the dimensions. The radius of the cylinder is 10 millimeters, and the height, you can, if you just label it h, that's fine, but a really nice insight is to notice that h is actually a function of t, and it's given by the function s of t. And with this little insight, you'll sort of get to some of the solutions a little bit quicker. All right, now we're ready to attack the problem, so let's go ahead and take a look. All right, part A, according to the model, what is the height of the water in the can at the end of the 60-day period? And so I know there are two contributors to finding s of 60, in other words, the height after 60 days. There is, of course, what the height is at the very beginning, and then there is the change in height between 0 and 60. And you can think of this sort of as being the displacement of the height. How much has the height changed? And so we can utilize the fact that the definite integral of the rate of change from a to b will give us the amount that that quantity has changed between 0 and 60. And since we know that the initial height, s of 0, is in fact 0, this is the only contributing factor to the height of the water in the can after 60 days. So we can say that the height after 60 days, s of 60, is equal to the integral from 0 to 60 of s prime of t dt. And if we do say that statement, we actually get a point there. So now integrating from 0 to 60, this function here, you can do this all in your calculator, or you can take the antiderivative and evaluate at 60 and at 0 in your calculator. Taking the antiderivative of this function is actually fairly easy. Antiderivative of 1.5 is 1.5t, and since we can split it up based on the sum rule, we'll then look here, and we notice that the antiderivative of sine is going to be negative cosine, because when I take the derivative of negative cosine, I get the antiderivative of cosine, which is negative sine, and the two negatives will counteract. So I know I'm going to have negative cosine of 0.03t. I have my 2 out here, so that's going to stay. But when I take the derivative of this function, I'm going to get a 0.03 thanks to the chain rule. And so I don't have a 0.03 out front, so I need a 1 over 0.03 here to counterbalance that derivative of the interior. So this is my antiderivative, evaluating at 60 and at 0, and then taking the difference, gives me 171.813, and that, of course, is in millimeters. So that is the height of the can of the water in the can after 60 days. All right, question B is actually a pretty straightforward and simple question. According to the model, what is the average rate of change in the height of water in the can over the 60-day period? Show computations that lead to your answer and indicate units of measure. So remember, average rate of change is simply the value at your endpoint minus the value at your initial point divided by the time interval. In other words, we're going to have the height after 60 days minus the height at the beginning divided by the time that elapsed, or 60. Okay, and if you thought of this, then you could compute this easily because we found the height after 60 days at part A. We know the height at the beginning is 0, and we can divide that pretty easily by 60. Before we compute that, I want to show you how this is similar to another way of thinking, which is you're finding the average value of the rate of change. And we have the function S prime of t that gives us the rate of change. So using the definition of the average value of a function, we can compute this same thing by doing 1 over b minus a, or 1 over 60 minus 0, multiplied by the integral from 0 to 60 of S prime of t dt. Because notice that this function here is the rate of change of the height, and so applying the average value definition will allow us to find the average value of the rate of change. Notice that this here is exactly s of 60, because s is the antiderivative of s prime, minus s of 0. Right? That's just the fundamental theorem of calculus. So either way, this is saying the exact same thing. And regardless, we've already computed this part here, right? We've already computed s of 60, which is exactly this. And we can multiply that by 60, i.e. divide by 60. And so regardless of how we do this, we'll get the same answer, which is 2.863 or 2.864 millimeters per day. And you'll get 1 point for having the correct value numerically and the correct units. Part C, assuming no evaporation occurs, at what rate is the volume of water in the can changing at time t equals 7, or in other words, day 7? So here we can identify that we're searching for the rate at which volume is changing, in other words, dv dt. And I can identify this as a related rates problem, A, because I'm searching for a rate, and obviously this rate is dependent on time, and this rate is going to be related to some other rates that I may already have. But I don't explicitly have a function for volume yet, so I'm going to need to create one. So I've got to identify what the rate of change that I currently know is, so that I can write an equation that involves both the variable of the rate that I know and the variable of the rate that I'm trying to find, which is volume. So if I look back, I'm trying to determine, well, what rates of change do I know? And I'm thinking about the options here. Well, the radius is exactly constant. The only thing that's changing is the height. Do I know dh dt? Do I know the rate at which the height is changing? And I do. That is exactly s prime of t. So I can write a function relating height and volume, and then when I differentiate, I'll be able to have an equation with a rate of change that I know and the rate of change that I seek. And so the formula for volume in terms of radius and height is v equals pi r squared h. And here I know that r, the radius, is always 10 millimeters, so I can square that and update my equation so that I have the volume is 100 pi h. Now, you can go ahead, you've already noticed the relationship, right, between the derivative of height with respect to time and the function that we already know. So at this point, you can go ahead and make the substitution that h is simply s of t, and when you differentiate, you'll end up with s prime of t. So you could do that, or you could go ahead and differentiate already, because we've already made the connection that we know dh dt, it is s prime of t. So let's look at both ways just to make sure that you understand what I'm saying here. I could at this point make the substitution of s of t for h. So my volume is equal to 100 pi times s of t. And at this point, I can differentiate. And so I'll differentiate both, and we'll see what that looks like. All right, so let's start with the left here. I differentiate with respect to time. I have dv dt is equal to 100 times the derivative of height with respect to t. And at this point, I can make the connection. dh dt is simply s prime of t. So then I can get to this equation here, which is the same thing I got by differentiating v equals 100 pi s of t with respect to t, where I get 100 pi times s prime of t, the derivative of s of t. So either way, I'm going to end up at this equation here, and now I can evaluate, because I can compute, thanks to knowing the actual function for s prime of t, I can compute dv dt at t equals 7. And doing so gives me 602.218, and these are going to be millimeters, and they're cubic because it's a volume, and this is per day, obviously because t is in days. So writing out my answer would look just like this. The volume of the water in the can is increasing, positive, at a rate of 602.218 millimeters per day. Part D. A lot of words here, and thankfully more creativity with the name of the location. We had Stormville, and now, drumroll please, I introduce you to Monsoon Mountain. During the same 60-day period, rain on Monsoon Mountain accumulates in a can identical, amazing, they have the same exact can to the one in Stormville. The height of the water in the can on Monsoon Mountain is modeled by the function m, where m of t is given by that polynomial. The height, m of t, is measured in millimeters and t measured in days, again, shockingly, from 0 to 60. They give you a function, let d of t be equal to m prime of t minus s prime of t. They want you to apply the intermediate value theorem to the function d on the interval from 0 to 60 to justify that there exists a time t between 0 and 60 at which the heights of water in the two cans are changing at the same rate. So a lot that we need to sort of pick away at. The first thing is that we can just create a replica of the Stormville can, and we can label the appropriate dimensions, the radius, 10 millimeters, and the height, which is equal to the function m of t, so it depends on time, and this is the function m of t, and that gives you the actual height. And the question gives you this function, d of t, which is equal to m prime minus s prime, and it asks to apply the intermediate value theorem to figure out when the heights are changing at the same rate. Okay, so there are really two key first steps aside from just annotating and drawing this can here, and that is to identify what in the heck d of t is actually telling you, and the second is to remind yourself what the intermediate value theorem tells you. So let's start with the intermediate value theorem. The intermediate value theorem is very simple, and let me draw a quick picture to illustrate what it says in case we've forgotten. All right, intermediate value theorem, very easy to understand. If I have a continuous function f on an interval from a to b, and we know the value of our function at a, in other words f of a, and we know the value of the function b, in other words f of b, then since f is continuous, the only way for it to get from the value f of a to the value f of b is to take on every single value between f of a and f of b. Pretty straightforward. And this can be applied in many situations to show that a function at some point crosses the x-axis. If we know that, say at a, that the function had a positive y value, and at b the function had a negative y value, the only way for it to get there is to cross 0 at some point. And so we're looking to show that our function at the beginning of our interval takes on a value that has a positive or negative sign, and then that the sign switches and it takes on the opposite sign value at the endpoint. And that will allow us to apply the intermediate value theorem to show that at some point our function is in fact 0. So how can this help us with d of t? Well, let's just quickly look at what d of t is. D of t is m prime of t minus s prime of t. M prime is the rate at which the height of the water in the can in Monsoon Mountain is changing, and S prime is the rate at which the height of the water in the can in Stormville is changing. So this is taking simply the difference between the two rates at which the heights are changing. So if we're looking for where the heights are changing at the same rate, well, these are their rates. When their rates are the same, d of t is going to be, you guessed it, 0. So to show that d of t must at some point be 0, we can evaluate d of t at the endpoints, and if the sign changes between d of 0 and d of 60 in this case, then we're in great shape. So we need to consider d of 0 and d of 60. All right, so for both of these, we're going to need m prime of 0 minus s prime of 0, and here m prime of 60 minus s prime of 60. Now you are given the function m, so you can differentiate m to find m prime of t, and then you can evaluate at 0 and at 60. So d of 0 turns out to be negative 0.675, And d of 60, thankfully, turns out to be positive 69.377. Well, we know that this value is less than 0, this value is greater than 0. So let's sketch out our argument here. We know that this function is continuous, it's less than 0 at the beginning of our interval, and it's greater than 0 at the end of our interval. Therefore, the intermediate value theorem guarantees at some point in between 0 and 60, d of t was exactly equal to 0, and therefore the heights are changing at the same rate at least once between 0 and 60. So here I have written, since d is continuous, d of 0 is less than 0, and d of 60 is greater than 0, the intermediate value theorem guarantees there is a time between 0 and 60 at which d of t is equal to 0, and thus the heights of water, the water in each can, are changing at the same rate. In other words, m prime equals s prime.